All right, if you think back to the electrochem unit, we discussed Q. And when we talked about Q, it looks a lot like, or at least the formula for Q looked a lot like the formula for K, because it was products over reactants raised to their coefficients. So it looks a lot like K. So what is Q? Well, besides being one of my favorite fictional characters from Star Trek, Q has a lot to do with K. Q is used to compare the concentration of products to reactants of systems that are not at equilibrium. So we can use this to compare to the K. If we know what the K value, what the equilibrium constant is for a reaction, we can figure out if a reaction is at equilibrium, or if it's gone past equilibrium, or if it's short of equilibrium. So let's look at each one of those scenarios. Problems where you'll be asked to do this will usually start by giving you the starting amounts, as well as a value for K. Because without a value for K, you can't compare it. You obviously can't compare your value of Q that you get with K. So anytime you're given a K value, or you're given starting amounts or different concentrations, you know that you're going to be asked in some way or another to calculate Q and compare it to K. And the test could be outright and say, hey, tell me what the value of Q is at this particular time. And then in a later section say, what does that mean in terms of the system being at equilibrium or not? Or it could do it quietly and say, predict which direction the system will shift. So anytime you're comparing your K and Q, I would recommend, because this is how I personally do it, I would write it in alphabetical order. K comes before Q. So say K, such and such Q. And this way, whichever direction the little Pac-Man faces, whichever direction the arrow faces, is the way that equilibrium is going to shift, or the reaction is going to shift. So let's look at some of these scenarios. You'll see what I mean in just a moment. If Q is less than K, that means that the system has not yet reached equilibrium. And therefore, the reaction will shift, or the system will shift towards the production of more products. See how the arrow in the Pac-Man is pointing towards Q? And that's the direction that we are going to shift towards the products. So the reaction will shift to the right, towards the production of products. If K and Q are equal, then our system is at equilibrium. There will be no shift, because it's not as though we're favoring one side or another. The rates have equaled out, and therefore we are at equilibrium. K and Q are equal. If Q is greater than K, that means we've overshot equilibrium. The reaction had so much energy it went way past equilibrium. It doesn't even have to go away, but you know what I mean. It goes past equilibrium, and therefore we're going to fall backwards. So we will shift to the left, back towards the formation of reactants. Sorry, I forgot to shrink my K. So if Q is greater than K, we're going to shift back towards reactants. And this is particularly useful when we're asked to predict what will happen under certain conditions, when we aren't exactly sure what's going to happen to a reaction. And if we know Q and we know a K, or we can calculate Q and we know what K is, we can compare them to one another and tell which direction a reaction will shift. So for the synthesis of ammonia, well, we know what reaction that is. We've seen that before. That's the Haber process. So nitrogen plus hydrogen gives us ammonia. At 500 degrees Celsius, the equilibrium constant, we're given a K here. So K equals this value. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. So notice we want a direction here. So we're going to say left or right. We won't say product, we won't say reactant. We're going to say it's going to go left, it's going to go right, it's going to go up, it's going to go down. It's going to go left or right. There really are only two options here. So we're given concentrations here, so we're going to use Q equals the concentration of ammonia squared divided by the concentration of nitrogen to the first times the concentration of hydrogen to the third. Then we can plug in these values, and that will give us a value for Q. So we plug these values in, and we find that Q equals 1.25 times 10 to the 8th, which is huge, and especially when we compare it with our K value. So let's set up our inequality, alphabetical. K is what to Q? K is less than Q. What does that mean? Therefore, we're going to favor reactants, and therefore we will shift to the left. You always want to be very specific. We're shifting to the left. Why are we shifting to the left? Because we're favoring reactants. Why do we favor reactants? Because K is less than Q. Always try to explain as much as you can. Don't over-explain. You don't want to shoot yourself in the foot, but you want to be as thorough as possible. Alright, on the next one, it's the same equation. Q equals ammonium over nitrogen divided by nitrogen times hydrogen, and we'll just plug in these values. Once we do that, we find that Q equals 0.06, which is pretty much what we have here with K. K is 0.06 as well. So what does that mean? Well, set up our inequality. Q is what to K? K is what to Q? K equals Q. Therefore, what does that mean? It means we are at equilibrium. Therefore, there will be no change in the reaction. Alright, last one. This is a short video tonight, guys. If Q is going to equal all of these, let's plug them in and see what's going to happen. Q would equal all that, which we come to find out equals 0.002. Set up our inequality. K is what to Q? We see that K is greater than Q. That means we still have a little ways to go before we reach equilibrium, so we will favor the production of products. Therefore, the reaction will shift to the right.